time. This is screencast up to this point, and it's on the web as well as the Mathematica notebook up to this point. So we need to find the global stiffness. The global force vector. If you remember, there's 12 nodes here, so we'll need to allocate the space for it, and we'll do that by making a constant array that's 12 long. And then the boundary conditions here are pretty simple. We're just going to evaluate at the top there at nodes 9, 10, 11, and 12. We're just going to evaluate that function at x along there. And remember, x is the total length is 3a, so each one of those increments is a. So we'll have f9 is equal to cosine, TO cosine pi x over 6a. Then we're going to evaluate that at x equals 0. F10 is equal to the same thing, evaluated at what? A. F11, same thing, evaluated at what?
2a.
Okay. So that just leaves on the end there, the four nodes 4, 8, and 12 are subject to t equals 0. So we can just say 4, 8, 12 equals 0. So if we take a look at what the force vector looks like. Okay, now we just need to, everywhere that there's an essential boundary condition, which means on all of those outer edges, we need to either drop it from the K matrix or do that thing that we've done in the past where you put the ones along the proper columns. And because I want to plot this when I'm done, that's what I'm going to do. It's, in my opinion, the better way to do this. So along the insulated boundary implies that there's no heat flux leaving there. It's perfectly insulated. So we're actually going to solve for those temperatures along that boundary. The heat flux would be some partial T, partial U equal to something. In this case, it's just equal to 0, so we don't have to worry about it at all. All right, so let's see. At K, the rows of the K matrix, 8, 9, trying to think of the best way to do this. I guess it's not that many, so I'll just do it by hand, kind of. So the rows of the fourth row of the K matrix, we're going to want that to look like this. And the 8th row, and then we can use that to help us finish. So the 9th row, tenth row, eleventh row, 12th row. I hadn't executed anything yet, so when I tried to execute that one, it complained. So now if we look at the K matrix, I got it. I see it. I'll fix it. So it's kind of a slow evaluate because it's reevaluating the stiffness matrix at the top there every time. But anyway, you can't see all of the matrix. It goes off to the right of the screen here, but that should be 1, 1, 1, 1, on down. All right. So we should be able to solve this. If you remember, when I derived the stiffness matrix, I did it in terms of A and B, but here the A and B are equal. So I can say K, I'm going to evaluate this with A equal to B first. That'll save a little bit of time in the computation. And I believe that to be correct. So finally, just so we can see what's going on, I'm going to just set TO equal to 1. So I'm just going to evaluate it to a number so that these are all numbers. And then I'm going to plot this. So I'm going to say list surface plot 3D. And I'm going to assume that while we didn't find A and B, I'm just going to define their links to be 1. Just so I need to put some numbers in there to plot it. So I'm going to plot the grid. So it'll be 0, 0, 0, 1, 0, 2, 0, 3. So it'll be 0, 0. I need to give this a value. Assign it a variable. So that's all 1, 0, 1. And I have to follow the node numbers so it'll be correct. So I have to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, because that's how my solution vector is listed. So now I'm going to go back up to node 5, which is located at 1, 0. And obviously, there's better ways to do this. You could automate it some such that you don't have to type it all in, but this is not that many. So now we get, so the height of this represents the temperature distribution. So it's interpolating between, and it's pretty coarse, right? Because we don't have that many elements. So, you know, this represents the x-axis, 0 to 3. This represents the y-axis. And then the height represents the temperature. So it's a way to visualize it. Another way might be a better way for this particular thing might be like a contour plot. So that it would be flat like a plate, but you could see contours of the different temperature distribution.